So my presentation is based on customer experience of customers trying to adopt UVM and the pains that people have during that adoption phase. I've called it resistance is futile because it seems the whole industry is, not the whole industry, but a vast majority of the industry is now moving across to UVM. Some of our customers are staying on Beckman, but a lot of customers are now moving across to UVM. What we're going to talk about now is some of the pain that we see from some of our customers who are trying to adopt UVM. First of all, a bit of background, which gives you some figures on the adoption of UVM in the industry. So these figures are from a study done on in the US. But it's a worldwide study. And it can show you there that the percentage of the total project time spent in verification is increasing. So now the amount of time spent in verification is between 60 and a lot of the projects, the median number of projects, is actually now spending most of 60 to 10% of its time in verification. Okay? The percentage increase in verification engineers is also expanding. So in 2007, the majority of people were in design. So each, on average, the project with 7.8 designers and 4.8 verification engineers. In 2010, design had gone up from 7.8 to 8.1. Verification had gone up 4.8 to 7.6. That's an average increase of 5.58% over those 3 years. So there's a vast increase in the amount of verification engineers that are on the project. So what it's leading to is what we're calling the verification productivity gap. And a lot of people are moving towards UVM in an attempt to fill that verification productivity gap. So we know that silicon density follows Moore's law. Design productivity can't keep up to use all of those transistors that you can put on your chip now. And verification lags behind the ability of design. I call this Murphy's law. But these are the trends now. So you can actually now see the trend within our industry, the adoption of more advanced verification techniques. So again, going from 2007 to 2010, the number of projects, percentage of projects using assertions has gone up from 37% to 69%. The number of projects using constrained random has gone up from 41 to 64%. Code coverage, 48 to 72%. And functional coverage from 40% to 72%. So you can see a huge leap in the adoption of some advanced verification techniques. A lot of these, all of these are supported by UVM. Apart from the one down the bottom where formal property checking is going as well. And that's going at a high rate as well now. A number of companies and projects are adopting formal verification techniques. But today we're just speaking about dynamic techniques and UVM. So UVM to the rescue. UVM is going to save our verification challenge. And you can again see some figures here that the adoption rate of System Verilog. Now, System Verilog is now the most popular, it's predicted to be the most popular verification language as Verilog drops. So in 2010, it would dip from 24% to 60%, while Verilog had dipped. So by 2010, System Verilog was already the most popular language, and it's growing. And Specman is beginning to dwindle. And UVM is predicted to be the most popular methodology as well. OVM is still growing, but now as UVM comes along, people are beginning to drop OVM and adopt UVM. Why? UVM basically has a very, very good pedigree. So if you look at this chart here, you can see the history of these languages and methodology. So in the bottom left-hand corner here, you can see where System Verilog has come from. It's come from a mixture of E, Avera, Verilog, and VHDL, and taken the best of those to create System Verilog. UVM is now the first industry-wide adopted verification methodology. I think ERM was probably the first one that people used. That was back in the 2000, that's 12 years ago now when I first started using ERM. Venture brought out AVM, and Cadence and Venture then agreed on OVM, and then Synopsys joined the game when they brought BMM into UVM as well. And UVM is now an accelerator standard. So if you look at that slide tells you that the main EDA vendors are behind UVM, which is really, and also it's been standardized. That's what's really driving the industry to begin to adopt UVM, because the top 3 EDA vendors are all behind it, and most other vendors are behind it as well. But the top 3 have adopted it.
Mike,
but what does it stand for? What does it? Yes?
Apologies, could I stop you there? I think you're holding the mic too close to your mouth. We're getting a lot of distortion.
Okay.
Thank you.
Okay. Is that better?
It's a little bit better. Yep, that's better, thank you.
Okay. So, UVM stands for Universal Version. I won't go into the details here, but it's very large. And if you go to a dictionary, methodology means a system of broad principles or rules from which specific methods or procedures may be derived to interpret or solve different problems within the scope of a particular discipline. It's not an algorithm, it's not a formula, but a set of practices. And what you'll find is that as you go from one company to another company, they'll be doing UVM slightly different. We've just had a presentation, a good presentation from TI, where they've used a particular way for the CPU to communicate with the IP. And other companies will adopt different ways. Even during the question and answers, rather than use weights, someone said use your error poll. So you can see within the methodology, there's lots of different ways of solving problems. And UVM is a set of practices, not a formula. So you go to adopt UVM, think there's a blueprint, and you have to interpret the methodology.
Apologies, Mike, I'm sorry. I'm sorry, Mike. The audio is fading in and out again. If you could hold the mic still, that'd be great. Thank you.
Okay.
That's fine. We still have the distortion, but it is louder. Thank you.
Okay. So last time I looked at the system Verilog LRM had about 580 pages. The UVM class reference guide is over 400 pages. That's 900 pages, or nearly 1,000 pages of specification of the language. And it's very, very easy to lose the consistent look and feel, write non-reusable code, and also to use the wrong level of abstraction. Those problems have always been around in verification. And I've seen good presentations for someone called Brian Hunter. He works for a company called Cavium. And I've seen him speak at 2 conferences now. His company has written a 180-page guideline on how they should adopt UVM. And that's just one company on their particular adoption of UVM, because it was too loose. And they found that across their company there was too much inconsistency. And they decided to write a 180-page guideline. 600 M, 400 pages of class reference manual, and 180 pages of guideline. So it's verification engineers have to do a lot of reading for that. And so I put a noose here. Basically, there's a lot of road, and we do see different adoption techniques as well. So why do we bother? If UVM's so hard, why would you bother? Well, the statistics show, as we've seen already, it's becoming a de facto industry standard. That brings advantages with it. So, for example, training is available. It means engineers become available. And there's also a community of help. So you can actually go onto some of these LinkedIn and ask questions, or some of these support groups and ask questions. You'll get answers to your questions. There's a lot of people out there who are willing and able to answer any System Verilog or UVM question. Importantly, though, the industry tools and VIP are adopting UVM. So, for example, mentors, every major simulator vendor will support UVM and port their VIP to UVM. So that means there's going to be a large library of verification IP available within that language. So whichever protocol you're working on, there's a good chance now that you can pick up some UVM verification IP for it from the industry rather than have to create your own. And there's a lot of advantages of using industry standard VIP. Means that your ongoing maintenance, you're fairly future-proof if the whole industry is behind it. There is an open source community. I know at least 2 companies who have written libraries and donated it so that other people can use it, and it definitely can do the job. We've used UVM on lots of projects. You've just heard how TI have found the ability to take block level verification IP up to SoC level verification, and also allow their CPU code, that C code running on the CPU, to communicate with their external UVM VIP. So you can do the job with UVM. But what we've seen is the adoption of UVM must be well planned. Otherwise you will find that all your projects write it in a slightly different way and your level of reuse drops. And remember, looking back to the picture and the verification gap, reuse is the thing, one of the things that's going to save verification and allow us to do it. So this is a particular company we've worked with. It's a company called Dialog Semi. It's a company based in the UK. They're very successful at developing power management chips that appear on a lot of mobile devices. So a lot of the problems they had. So one of the issues they started with was that a lot of their engineering base was RTL-centric engineers who understood VHD on Verilog, but never learned OOP concepts. If you want to get into UVM, you have to understand object-oriented programming. And a lot of our industry have not come from that background or that discipline. The Verilog engineers never have learned. They found that as people write their UVM environments, and this isn't just UVM, you potentially get the same problem in SpecMan. It's very hard to get your constraints right. And it's very difficult to know if you've got them wrong. Have you over-constrained? If you over-constrained, you under-verify. If you under-constrained, you get false bugs. Getting the constraints just right is actually quite difficult to do, but that's a problem with constrained verification, not a problem with UVM. You can have the same problem with Spec. Writing a good reference model is very difficult. Writing it with the right, like your checker or your squabbled at the right level of abstraction. They found that a lot of the designers were writing helper code that looked into the RTL in order to trigger the right checks. So their checks were actually based on some knowledge from the RTL. So it was difficult for them to judge how independent that scoreboard logic was, because it was actually poking inside the RTL. Difficult, dangerous use of configuration settings. Set config in star has big ramifications inside your UVM environment. And then slippage between VPlan and coverage model. The early project did not use the agent easily. It was too tightly coupled to the original interface on the first project. A module to chip reuse is not trivial, and we've just seen that from the presentation from TI. That was one of the issues they had, how to move module level VIP up to a chip level verification. And there are some issues there. And we've just seen a good paper on one of the solutions to that problem. Some solutions, encapsulation of VIP settings and configuration objects. That's good standard UVM practice. Encapsulation of BM tasks, plus functional model tasks in the interface gives you a much better reuse model for derivative DOTs where the interface is changing. Structure of scoreboards for use and decoupled checks. MVC is actually a very software pattern. I won't go into that now. Leverage common sequence API. So, for example, if you're doing register-based stuff, there is now within UVM some register-based libraries available based on register abstraction level, and those libraries are very useful for leveraging in your register read-write verification. And what they also did on the bottom slide there is a multi-layered approach to verification. They structured their teams into people who develop the infrastructure and the verification IP to those people who are actually doing the project-specific stimulus. So the skills needed in those teams are different. Infrastructure and VIP development requires deep knowledge of UVM, system Verilog, and VIP constructs, whereas the project requires people who have good use case knowledge and knowledge about the target chip. And they split their teams as such, so people between system Verilog experts and the use case experts. They also had a structured rollout that took people from novice to training to expert. They used external training, internal seminars and knowledge sharing, so people would write up their experience and share that. They used external OVM resources. They used OVM forum a lot. As I said, there's these forums that people, they can ask questions and get responses, and external consultants. And they introduced it on live projects in a controlled way. They had a pilot project for it. They learned the lessons of that pilot project. As the new projects came on stream with new people writing code, they made sure they did a lot of code reviews to ensure the code is being properly written. And they're building up a library of OVC components which they can reuse across a number of projects, and making sure that those OVC components are written in a much reusable way using the OVC construct. So conclusions from dialogue on the adoption of OVM. This is OVM, but the UVM is very similar. They had a high. They discovered more bugs basically. So as they moved from the direct verification to constrained random, they found more bugs, and they found it easier to track real progress through coverage and functional coverage. They found that a better way to track real progress rather than the number of direct tests they'd run. They found that OVM or UVM now, they've now moved across from OVM to UVM. We won't initially reduce your verification effort. On the first project, there's a lot of infrastructure to be built, but on the second and third project, that infrastructure starts to pay back, and the increased reuse leads to cost savings. They had a lot of directed tests, which they didn't want to lose, so in that situation, they used the OVM in passive mode. That allowed them to do protocol assertion checks, protocol checks, and collect functional coverage, so they could see how much functional coverage those legacy tests actually achieved. And the engineers who were working at the top level, who were writing the tests, the ones with the use case knowledge, were able to get going relatively quickly. When you get to the test level, and you're calling sequences, the concepts at that level are less difficult for those chip level experts to understand, because you've abstracted by that point a lot of the UVM system detail to a test level. So that last part was about structuring your teams like your test benches. So what you can see here is how you can construct your test bench, and down at the bottom is where I'm saying, as you write the test suite, there you're looking more at use cases, but you're only communicating with the virtual sequencer, which has abstracted a lot of the detail in system Verilog and UVM. And Dialog found that their chip experts were able to work at that level of abstraction very, very painlessly, and adopt it very quickly at that level. So let's just put this in context. UVM is not the complete solution. Just UVM allows you to build great test benches. So you have to have good sign-off metrics. You have to develop good functional coverage models. You have to measure the checker quality. I'll have a slide on this in a minute. You have to develop a verification IP strategy and a reuse strategy, and whether you integrate it with formal or not. Let me just talk about a couple of those points. So you still need a very good verification plan. The fact that if you adopt UVM and start writing UVM test benches does not mean that you're going to get better verification. You still have to plan your verification, and you still have to, your verification is only going to be as good as your verification plan. The mechanisms of the mechanics of finding the bug, if there's your DUT, and there's a bug in that DUT, well, you have to fire the right sequence of the right sequence to hit that bug. So at some point in your verification, you hope to stimulate the DUT in such a way that you hit that bug. But then that bug needs to be propagated to an observation point, and your observation point needs to be able to spot that there's a miscompare. And what we find is companies find it difficult to have all three of these. Maybe they can write very, very good stimulus, but if they're not doing enough checking, they won't find the bugs. They may have very, very good checkers, but if they're not doing enough stimulus, they won't find the bugs. You have to have everything in place to find those bugs. And as I said, part of the reason for adopting this is to increase verification reuse. So why do we need, and this is done a lot through verification IP. And why do we need VIPs? VIPs should increase your time to market. They're ready to integrate models to accelerate your development. So as you develop your RTL for a new interface, you should be able to go and pick up verification IP from the market, which allows you to verify that RTL rather than have to wait to develop your own test bench. If you're picking up VIP from the marketplace or even internally, as you use those verification IPs across multiple projects, the quality of that verification IP will increase because it's getting reused by more and more people, and they add value to it. And it should reduce costs as well. As you increase reuse, you reduce costs. And as I said in the paper we had previously from TI, you can see they had vertical reuse. They reused their verification IP at block level up to stock level. Okay, so they've already got reuse. They've already saved money on that project from that verification IP. Horizontal use is they move from that verification IP across multiple chips. They get cost reductions through horizontal. But there's also industry reuse, where as you go into the marketplace and you try and pick up verification IP, you should be able to get out cheaper to license. And I know that as a Cadence customer, there'll be verification IP that comes with your Cadence environment. So verification IP improves our time to market, should improve our quality, and should reduce our cost. Allows us to start closing that verification gap on the design productivity. So in summary, UVM can do the job. It's a job of building constrained random verification libraries. That's the job, but it's not easy to learn. It's not easy to do, and it's a huge language. It's a huge methodology. Without proper ramp and proper adoption policy, you'll find that your projects use it in slightly different ways, and you won't get as much reuse as you expect. And it's not a silver bullet. Okay, it allows you to write good test benches, but that doesn't mean you're going to write good test benches. You still have to be a good verification engineer who understands how to write a good test bench, and you have to understand how you can maximize reuse from it. But it is a very good step for our industry. At last, the industry's got a unified verification language, a unified methodology, and I think over the next 3 or 4 years, 5 years, we'll see quite an explosion in what's available in the marketplace inside UVM. Okay? So open up for questions now. Any in the room? Yes. So the question was, UVM is still evolving. So where would we see the improvements coming from? So the last big improvement I saw was the rolling of VMM. I think it was release 2.1 or 1.1. So when a Synopsys joined OVM to create UVM, and a lot of libraries came into play at that point. A lot of new libraries. So, for example, they brought in improved register abstraction. So I think the libraries will continue to improve. The thing I think we're seeing at the moment now is libraries to help locale verification. So I think what I see coming from the Shadow Committee is improved libraries. I think the user community will increasingly donate libraries as well. So I recently saw a library from a service organization that allowed you to more easily reach out to RTL signals in a way that then could be reused from block level up to system level. So as you move from block level up to system level and you refer into signals, you're probing into signals in the RTL, their library made it easier to move around the hierarchy. So I think there will be more user-defined donations, if you like. But what I see that DVM's doing is responding more quickly to our industry challenges. I'm on the SpecMan language group, and we're not responding under SpecMan as quickly as UVM responds to the challenges. And power verification is a good example of that. So there's a library that helps you do low power verification coming out in UVM. SpecMan's not, the E language hasn't planned that yet. So I think more and more libraries will come out to make it easier to verify the challenges we see in the designs we get. Another one might be, for example, mixed signal, analog mixed signal, and UVM, a library that can specifically talk to analog mixed signal design, do that type of verification. But I think at the moment, what I see is libraries coming out to hit specific verification challenges. Any other questions, Sarah?
Yes, we have two questions. First one is, what is the difference between UVM and...
Okay.
Hi, sorry, I wasn't sure if you could hear me. The first question is, what is the difference between UVM and OVM methodologies? Which methodologies is used most?
I think you saw in the earlier slide that OVM is still the most popular, but UVM is now catching up. And UVM will overtake OVM. The major difference between OVM and UVM was in the last release, where the number of phases was increased a lot as VMM was adopted. So it was the merger of OVM and VMM brought a lot of new features into UVM from the VMM library that didn't exist in the OVM library. And the two most popular ones I've used are in terms of register extraction and the build phases, the number of phases that you go through from build to run phases. And there's a lot more of those phases where explicitly in UVM, but over time the UVM will actually, I think, in 2 years' time, I'm sure that OVM will just drop away and most people will be UVM. There's no... UVM is a superset of OVM, so why would you stay with OVM? I think it's just at the moment people are still have projects on infrastructure in OVM which they need to just port across to UVM. When UVM first came out, there was a script that allowed you to take OVM into UVM, but that was, I think it was just a global replacement of OVM by UVM because there wasn't much difference. But now it's slightly more sophisticated. The OVM will still work in the UVM environment, but you're starting to lose some features within the UVM environment which don't exist in OVM. And as I said, one of them is the explicit there's more explicit build phases in the UVM environment. And I think as people will slowly move across to OVM, to UVM from OVM. Sir?
Lovely, thank you. Two more questions. The second question is, what is the benefit of getting the status of standard for UVM by Accelera or any other organisation?
What is the benefit? Okay.
I'll repeat it. What is the benefit of getting the status of standard for UVM by Accelera or any other organisation?
I'm not sure what you mean by status. It's an industry-wide release standard. So the benefit of getting the LLM is the language definition. So if you really want to know what a language construct does, then the LLM is the golden reference. And if you want to understand the language in detail, then you should use the LLM. I'm not sure what he means by get the status of it. Just go to the latest release of the LLM, and that's the language reference menu. That's the golden reference. So that's why it's valuable.
Thank you, Mike. One final question. There's a question whether Cadence is supporting all of the constructs for LRM.
In the room. The Cadence support all the constructs in the LRM? I'm just asking that to the Cadence person in the room. Do Cadence support all the constructs within the LRM? We have it's a marketing person, but most marketing people say yes. But he's an honest marketing person. He says he doesn't know. I think you'd have to ask that directly to your Cadence support person. I know that when OVM first came out, both Mentor and Cadence had some holes in their support, but those holes have been very quickly filled. So my guess is that most of the features that you'd want to use are supported. I've never been stuck on OVM or UVM because a certain construct wasn't supported. Is anyone else in the room? I don't think. I think it's a non-issue. Have you ever seen it from? The language is big, but with most of these things, when you develop your environment, you're using a very small percentage of the language. It's 600 pages. You can't learn all the constructs anyway. You use we say in the UK there's a 20-80 split. You use 20% of the constructs 80% of the time, and they're supported. So I don't know, as I say, Cadence guy doesn't know for definite, but in my experience, I've never come across that as a problem, because most of the constructs that when you develop in the UVM environment, you're just using a small subset of the language, and that's well supported. And that's well supported across all three vendors. So it means your UVM environment should be portable between all simulators. Okay.
Thank you, Mike. We've had one more question in. Was there any benchmark done by VCS?
Any benchmark done by VCS?
VCS, yes.
So you're asking, is this a Cadence versus VCS benchmark? I'm sure the marketing person would have an answer for that one. But I don't know. I'm not sure. I've seen any public figures on the simulators versus each other. So I'm not aware of any public figures for that. I've never had a real problem with simulation time there. So I've used VCS, Questa and CSIM, and I don't think I could point to any one of them and say, oh, it's much slower. I don't think simulation speed's the major issue. But to answer the question explicitly, I'm not aware of any industry benchmark that's available. It's quite hard to get those benchmarks publicly. And a lot of companies I know do internal benchmarks, but that's usually done under very, very strict NDA confidentiality agreement. And you're not, so if your company is concerned about that, what most companies will do is do an internal evaluation, calling all the events. Okay?
Thank you, Mike. We lost your audio just trailing off at the end there, but there are no more questions from the webinar.
Okay. Okay, so just remind to say thank you for dinner for Tax Instruments for his talk, and thank you for coming. And we'll tell you when the next one is. So thank you very much, and thank you to Cadence as well for hosting us today. Thank you. Thanks, Sarah.
Thanks, Mike. Have a good day, everyone. Bye-bye.